My name is Pradeep. I'm a production engineer at Facebook. And today I'm here to talk to you guys about how we do kernel upgrades at Facebook. So first of all, before I begin with my presentation, I want to take this opportunity to thank the SREcon committee and the program chair for providing me this opportunity and inviting me here to talk to you all and be able to share with you. And this is the first time I'm doing this, so I'm really, really excited, and hopefully it goes well. So yeah. So let's begin. So to give you some context, so Facebook has many geo-distributed data centers across the world. And these data centers run tens of thousands of servers. On each of these servers, we host a wide variety of applications from front-end services to news feed aggregators, live video applications, messaging, caching infrastructure, databases, and many more. One of the important things to note here is that all these servers need to have the right kind of software so that these services can run efficiently and smoothly. And one of such softwares is the kernel itself. So we have to ensure that you have the latest and the correct kernel for the services which run on these machines. So the main goal of my presentation today is I'm going to talk about why is it important to upgrade kernels. I'm going to talk about why we have to invest in building an automation to do this, so you don't have to spend time or think about it in the future. I'm also going to talk about the goals of the automation which is required to do this kind of operation at scale in a safe and reliable way. And I'm going to talk about how we did this at Facebook and the lessons we learned from the mistakes through the automation. So why is it required to upgrade kernels? The first thing which comes to my mind, the topmost priority is security bugs. So you have a lot of vulnerabilities which often show up in kernels, and it is important that you patch them soon enough so that bad actors don't take advantage of this vulnerability and cause unintended consequences for your production environment. So the most recent examples I can think in this space are about the meltdown and Spectre, as you all know about. As with any given software, you have, of course, bugs. And we saw a wide variety of bugs in our production fleet, ranging from allocation stalls, CPU stalls, stream stalls, and so on and so forth. And for our services to operate smoothly and have reliable uptime for them, we need to install kernels which have the bug fixes for what we saw. And that is why we have to upgrade kernels. New features. So you would be interested in trying out certain specific features, things like cgroups v2. So in 4.11 and 4.16 kernels, you have metrics on how your C group is being throttled based on the resource constraints you have set. You may have new firmware for your devices, general stability improvements. So that is why you need to update your kernels. And yeah, lastly, performance. General speedup is always good. So if you need better performing kernel, you would need to do upgrades. OK. So I'll pause here and tell you why we thought of doing this. So this is one of my first projects which I worked on at MySQL. I work for MySQL infrastructure at Facebook. So this is one of the things which I started to think about. So MySQL is a stateful service, and it's one of the primary data stores, which is the backend for the Facebook Graph database. Doing kernel upgrades on stateful services, the machines which host stateful services is tricky, right? So for example, if you have a master on host, you need to ensure that you promote it away to another data center before you take that host down for maintenance. we have a service discovery framework at Facebook, which all the clients use to figure out where do I have to connect to, which machine I have to establish my TCP connection to, get my data. So we need to make sure the service discovery framework is updated reliably so that the clients don't connect to it when the machine is down. And given the Facebook scale, how do you do this in a safe and reliable way, right? So yeah, so this is why I started thinking about what is this common goals we need to have in this automation so that everybody can benefit and adopt it and make this pain-free process. So let's talk about the goals of the automation, right? Like how do we build this? So the first thing what we need to do when you are taking a machine for a kernel upgrade is what needs to happen when you basically shut down the machine. So things like, for example, in MySQL, if you have a master, you have to promote it away. If you have a service discovery framework, you need to make sure that you disable these, update this to not have clients connect to it. If you have host level monitoring and alerting, which you have enabled, you probably need to suppress it because the host is going offline for an upgrade. So this is where most of, we can call this as a maintenance handler for your host. So this is where all the things happen when you take down the machine for upgrade. The second thing, I call it as the orchestration. Here, you have to think about concurrency controls. How can you do your upgrades? Can you do your upgrades parallelly, serially, or per rack, per data center, and so on and so forth? You think about rate limiting. You do not want to upgrade too many things at once and causing service disruption. You have to think about kill switches. So if something goes wrong, you need to have a global kill switch to stop it and not cause more production problems. And yeah, so you should be able to have some sort of language where you can express all this information, and your automation can understand this. The next step of this, the automation framework is continuous deployment. So what I mean by this is, all the service owners should care about is what kernel version I should be at. And they just specify that. And the automation's job is to make sure that it converges to that desired kernel version eventually. And that is what service owners would only do. They'll just change the config, say, hey, I want to be on 4.11 FBK 19. So just the automation should pick it and try to converge to that point. So it should be very continuous. And lastly, with any good automation framework you build, you should have solid monitoring. So what I mean by this is you should have ways to, you should have a place where you report all the information from this upgrades globally to one place. You should be able to visualize this. You should be able to aggregate over this data and have useful inferences from it, so you can debug and figure out what's going on with the automation. You should also think about having some sort of a time series database. Time series view of things, so you can tell what is happening with the automation. Good CLI tools to interact with the automation. So if your on-call is paged for this and you want to debug what's going on, you should have good CLI tools to probe the automation and figure out what's going on. So this is where you would think about all those problems. So now that I've told you guys about what are the goals of the automation, let me tell you about how we incorporated all this and what we built at Facebook. So let's call this as kernel upgrade framework for simplicity. We have code names for projects internally, but yeah, this is a public talk, so let's call it simply kernel upgrade framework. Uh, so, what does this comprise of? It's basically a set of continuously running jobs, which are basically Python jobs. So at Facebook, we have a job engine framework, which allows us to implement a state machine where you can write custom code to do things which have states, and each of these states could be retried, and you can track the transition between these states. So it basically uses that framework to implement this automation for kernel upgrades. You can control parallelism. Here you specify, do you want global upgrades parallelly across all the clusters, per data center, per rack, and things like that. All of this is unattended, so it just works. We get notified when things are not going well. We have the ability to, this is the kill switch bit, we have the ability to pause, continue, and disable the automation globally per host prefix and whatever granularity you want. And we also support a concept of sharding. So what is sharding here? So here you have the option to canary different versions of kernels in production, so you can do some sort of A/B testing to figure out what works best for you. And this is where different services find out what version of the kernel they have to be at. OK. So, OK. Yeah, so this is basically a state machine which goes through one single host upgrade. I'm going to go in detail about what happens in each of these stages. All right. So each of these flowchart bubbles are Python functions. And this is the state machine which I mentioned earlier. So each state here could be retried. And you can configure delays between each state transition and things like that. All of this information is persisted in some database. And so this is what the upgrade looks like. So first, let's assume like you're upgrading a host X for a kernel upgrade. In the verify alive stage is where you figure out if this automation framework of yours is able to reach the machine via SSH, and it's able to connect to it. Once you verify that, we move on to the pre-drain stage. Here, you think about whether, can you take this machine offline for an upgrade? Are we being rate limited globally? Is it adhering to all the concurrency settings we have defined? Once you have all the safety checks pass, you transition to the drain host stage. So drain host stage is the only stage where the service owner would write their custom maintenance handler. And this is what would dictate whether, what needs to happen when the machine goes offline. So for example, in MySQL infrastructure, what we do is we basically promote all the master survey, if any, on the host. We disable all the MySQL instances in the service discovery framework so the clients don't connect to it. And once we do that, we respond, OK, you can take this machine offline for upgrade. So yeah, so it waits for the drain to complete. And we move on to performing the action stage. The action here is nothing but installing the kernel version which you want. So it's basically an invocation of kernelctl install kernel X. So once that happens, we poll for the action to complete. So the action here is basically you install the kernel and you send it for a reboot. Oftentimes, the machine doesn't reboot in time, so you can specify a timeout. Say, hey, wait 700 seconds before the machine comes back. If it doesn't come back, let's power cycle it. So you can control all that things via the config as well. And once the machine comes back online, we enter the verify stage. And in the verify stage, you install, like, did it come back with the kernel version which you wanted? And once you verify, you move into the unrange stage. So what's the unrange stage here? This is the other part of the maintenance handler. So this is the thing where the service owners would write their code, what needs to happen when the machine boots back up. We re-enable all the instances which we disabled in the service discovery framework. We bring back everything online. And then once we confirm that everything is good from the service side, we respond OK, and we do some sanity checks, and then we mark the upgrade as complete. So there are various failure cases in this entire flowchart, and for each of those failure cases, we fail the upgrade, and we have an ability to retry it again after a certain cooldown period. All right. So let's talk about the language specification, which I mentioned earlier. So the service owners would just define something like this in their config. They would specify, hey, what host prefix they want to upgrade. There are a variety of fields here. So for example, at once is a decimal value between 0 and 1, where you tell what percentage of hosts you want to upgrade at once. Parallelism is where you control how do you want your upgrades to be, whether you want it serially per data center, serially per rack, or you want it globally parallel, things like that. Constraints are more granular controls for service owners, where they can define like very specific constraints, like if they want to upgrade only a certain set of hosts, not everything in that host prefix, so they would use this constraint. It can be as arbitrary as you want. I'm going to talk about more examples later. So if you take a look at this constraint, this is basically saying in data center 1, upgrade clusters 1, 2, and 3 serially. You can also specify constraints like this. OK, so that was parallelly. Sorry, this is serially. You can upgrade clusters in data center 1, clusters 1 and 2, one after the another. And you can also have constraints like this, where you have 2 data centers, DC1 and DC2. And in each of these data centers, upgrade those clusters serially. So as you can see, this constraint fields is very flexible, and it can be a Python function as well, which can return the list of hosts which you want to upgrade as well. So this language makes the service owners, provides flexibility for service owners to define how they want to do their upgrades. All right. Let's take a look of an example config we have in production. So here it says that we have a host prefix called foobar. And I have defined the parallelism as cluster. So what it means is get all the clusters of Facebook and find foobar hosts, upgrade them at 1% concurrency, meaning at any given point of time, only 1% of the hosts will be offline, and the automation would respect that constraint very strictly. I also specify something called as the shards. Here, I am trying out 2 different kernel versions, 4.11 FB standard RC, release candidate, and 4.16 official version for 5% and 1%. And I can also pass arbitrary arguments into the automation itself. And this is where you specify things like, how long do you have to wait before you have to reboot the machine? And it can be arguments to your maintenance handlers and things like that. OK. As with any given automation development, you would definitely hit production issues, right? So I'm going to highlight a couple of them and tell you about how this exposed bugs in our service dependent, who use a service, and also talk about how it exposed problems in our infrastructure as well. So the first thing what happened is we figured out that when we were doing kernel upgrades, a dependent service of ours was not following the updates to the service discovery framework. So they were still trying to connect to the host, which was offline. And it so happened that one of their modules had a cache, and that cache was not following the updates to this service discovery framework. And the reason we found that was because we were doing these upgrades a lot more often, and that kind of exposed that bug for us. We also saw a problem where we learned the rate limits of other dependent services in context of MySQL. So we figured that out, that if we did way too much of upgrades, they just couldn't keep up with the number of instances which were offline. So from this, we were able to learn and add alarms and stuff based on these problems we saw, and gave us a good view of how our dependent services work when we take something offline. I talked about adding graphs earlier to visualize your kernel upgrades. So this is a time series graph I have here. And it shows what are the different kernel versions in the fleet for a given host prefix across time. Here you can see that this is probably the point where someone landed a change to the config file to say that I want kernel version X from now on, and a bigger percentage of it. So that goes on increasing, the other version goes on decreasing. So this helps us watch out for anomalies and explain things on what's happening in production. We also have a way to, this is again time series database, time series basically, which helps us visualize the rate of upgrades. So by this, we make sure we're not doing too many upgrades at once. And if someone asks or on call, like, hey, what's happening? Why are machines offline? So you can correlate the information accurately, and helps us in debugging as well. These goals are not just specific for this automation. You should think of this kind of visualizations for any automation you would develop. And yeah, so the takeaway is you should invest time in designing automation to upgrade your kernels if you don't have one. You should seriously think about this problem. And we have done this and tested it and proved it that it works. And we have not found any major concerns doing this in an automated fashion. And this is a solved problem for us now, and all we have to do is just keep up with all the kernel versions which our kernel team releases every month, and our hosts are automatically upgraded, and we don't have to think about this problem anymore. Yep, and thanks for providing the opportunity again and listening to me.
We do have some time for some questions. Whoa. Maybe just two.
Lunchtime. Toughest time to be here.
Hi.
Hi.
I got 3 questions. I'll try and pick one. This will fit a Facebook scale company where any one server isn't a dependency, but do you think this could work at a smaller scale where you've got Snowflake hosts or maintenance windows? If you could only run this in a weekend 4-hour time slot, would it still work at that scale?
So the question is, how does this work at a smaller scale where you have snowflake machines where you cannot take them offline at all, and you have specific time windows. Yeah. So I definitely agree that, remember the phase where I talked about, what should happen when the machine goes offline? We should in this case of yours, we should probably do a thorough analysis of like what needs to happen, and if there is an alternative to do this, you should probably figure that out and have some sort of a high availability for that machine or service which you're taking offline. And this is an opportunity to do that work as well, in my opinion. Yes?
How would you deal with kernel updates that have a significant performance impact, like Spectre and Meltdown were recently?
So the question is, how did you deal with kernel upgrades which have performance impacts for Spectre and Meltdown? So we have a kernel team at Facebook, and they evaluate all the fixes we want in our kernels. And when they say, hey, this kernel version is really good, we just use it. So I don't have specific insights into how that decision is made. I can find that out for you later.
Maybe we can take another one, if there is one.
That's it? Yeah. Thank you. You can all go for lunch.